What I'm going to talk about next is a Fisher projection. Now, with a Fisher projection, okay, I'm going to show you a way that you're going to represent these in a fashion that's a little bit easier. So, if something is pointed up and down on a flat plane, right, that means it's going away from you. If something is pointed left and right on a flat plane, it means it's coming at you. So, if I were to take one of these molecules again, let me borrow your molecule for a moment, and you're going to see that this requires a little bit of distortion, okay? So, if I want to put the hydrogen pointed away from me, one of the ways that I might express this would be to say, here's the carbon, and I'm going to point the hydrogen away from me. Notice the hydrogen is pointed away from me over here, and here's the carbon that's right here. In this case, the chlorine is pointed at me, so this would be like this, and the bromine is pointed at me, so this is going to be like this. Notice that what else is pointed away from me is the other carbon, right? So there's a hydrogen here, and now we have a CH3 here, right? Everybody's clear about it? So effectively what we're doing, thanks, I'm going to break it. Is we're doing this, right? Okay. So far so good? Okay. That projection, instead of writing that like that each and every time, becomes simplified by doing this. These are the same. Okay? So far so good? It's easy, except there's an important rule. Okay? I'm allowed to turn this 180 degrees, and it's okay. 180 degrees would be this would bring this down here, right? And this would bring this over here, right? You're not allowed to turn it 90 degrees. If you turn it 90 degrees on a flat plane, you actually get the other image. And you can see that if you turn this 90 degrees, I'm not going to take it. If you turn this 90 degrees, these two pop out and these two come back in. So you need to have this consideration of which way you're playing with the Fisher projections. How are we doing? Everybody okay? Any questions so far? Okay, so now let's jump into one more piece of jargon, I guess would be the right word. So this is a Fisher projection. You're going to get very comfortable with them right away. So that's a hint.
Yeah.
So these particular items, if we are going to express these as mirror images, etc., then with a Fisher projection, like this, for example, we have H, we have Br, we have Cl, we have CH3. So now if you're going to write the mirror image, all you have to do is this, right? Br, right? Cl, H, CH3. So this is the mirror image. Everybody okay with this? Any questions? Okay, so now I want to get you, since everybody's zipping along at this very nicely, I want to get you into one more comfort zone. Okay? Let me borrow yours for a moment. Here's that structure, and let's see which one of the two that we have here. If I take this hydrogen is pointed away from me, and the methyl group is pointed away from me, and no, I have this one, right? Because here's the bromine, here's the chlorine. Chlorine is green, bromine is red. Here's the hydrogen, here's the methyl group. Everybody okay with this? With me? Okay. So now, I want you to grab it again by its hydrogen, so that the hydrogen is pointed away from you and you're staring at the central carbon. Okay? Now if you're staring at the central carbon, you see actually 3 items, right? And what you see in this situation is like this. You see a bromine, a chlorine, a methyl group, and a hydrogen. Right? Now, if we have a method of examining these and assign a priority, the simplest priority is the group attached, the atom attached directly to the carbon, which has the highest priority, has the highest atomic mass. Okay? So in this case, it's bromine. And if we then have something that has the next highest atomic mass, that's chlorine. The next highest atomic mass is carbon. And then we have, the lowest one is hydrogen, right? So if we look at it from the standpoint of examining this from a situation of which one is pointed in which direction, then we can assign them a priority which allows us to look at it in the form of a clockwise or counterclockwise rotation. And if you're wondering what page I'm on page 173. Okay? Now, here we go. You got it by, this is a simple one, you got it by the hydrogen. What's the highest priority here? The bromine, right? So this becomes number 1. What's the second highest priority? Chlorine, that's 2. The third highest is carbon. So it's rotating, in my case it's rotating which direction? Clockwise or counterclockwise? Counterclockwise. That means it is S. Clockwise means it's R. It comes from the Latin term meaning R was rectus, I think, which meant righteous. And S is derived from the same Latin term which we refer to as sinister. People who were left-handed, by the way, in the Roman Empire, the Byzantine Empire, were considered sinister because the right hand was the hand of, we'll get into religious aspects here real fast, but you get the idea. So, if it is rotation with the clock, it is R. If it is rotation against the clock, it is S. Got it? Questions? Yes?
How do those relate to biology's L and D?
Good question. The answer is they are related by virtue of a structure known as glycerol. And L and D is convenient for a class of items. And the class of items could be construed as L or D. And inside that, there may be R and S items. And to be honest, we'll deal with L and D on the basis of, we'll get to it. I'll show you exactly what that means here as soon as we finish with Fisher projections. Who did I steal this from? So, now, remember, I had built this one right here. So, remember on the Fisher projection, this was pointed away from us, up and down. So this one was 1, right? And this one was 2, right? And this one was 3, right? So 1, 2, 3. That's what we need to count. Everybody with me? So that becomes S, right? So therefore, if we count over here 1, 2, 3, then this one is obviously R. Everybody okay? Any questions? Let's do one more just to make sure. Suppose that I gave you a structure that was like this. Okay, is that R or S?
S.
You say it's S? How many say it's S? How many say it's R? You say it's R? Well, what's the biggest group? So that's 1. Second biggest group? 2. Third? So which way is this rotating? So all of you say it's S. Ah, but the hydrogen is pointed out at us, so you have to reverse it. So that means it's R. So if the hydrogen, you have to grab it by the smallest group and point the smallest group away from you and then look which way it's going. If the smallest group is pointed at you, then whatever you got, it's just the opposite. That's the simplest way of remembering it. Doing okay? Yeah, for achiral there is no R and S. Okay? For achiral there is no R and S because there's no chiral center, right? How is everybody okay with this?
Can you go over that last one again?
Which one? This one?
Yeah.
Okay. Priority of groups, okay? This is number 1. This is number 2 because of the atomic mass. This is number 3, right? So far, you're comfortable. This is obviously number 4. But here, these 2 groups are pointed out at us, right? And these 2 groups are pointed away from us, right?
Yeah.
In order to determine R or S, you always have to have the smallest group pointed away from you. In that case, it gives you an immediate R or S configuration. If the smallest group is not pointed away from you, but it's pointed at you, then whatever counting you have, like in this case 1, 2, 3, which is going counterclockwise, it would have been S, but since this is pointed at us, it's just the opposite, so it's off. Other questions? Yes,
Is that
ma'am.
always true? Even so, we can't write that at 90 degrees.
Ah,
Because
you
we're
want to
not
write
allowed
this at
to
90?
write.
Should we write this at 90 degrees? Okay, I'll do this. You ready?
Yeah, just to be sure.
Okay, here's the CH3 is going here, right?
Yeah.
The H is going here, right? The Cl is going here, right? And the Br is going
Okay.
up there, right?
I just thought we just could turn it.
Okay, that's a 90-degree turn,
Yeah.
right? But you ready? So let's add them up then, okay? The lowest group is right here. The highest group is right here. The second highest group is right here, right? The third highest group is right here, right? So it goes 1, 2, 3. It looks like it's S, right? Except, which way is the hydrogen pointing? Is it away or towards us? So is it S? Notice we've made the mirror image. Are you confused?
Yes.
Good. Think deeply into the plane.
Are you supposed to switch it if the hydrogen's pointing towards us?
Say again?
Are we supposed to switch it? It's going S, but it should be R because the hydrogen's pointing over.
Ah, is the hydrogen pointing at us now?
No,
Up and down is,
it's away.
that's correct, that's all you
okay.
care about.
Up and down is away. Yes.
No,
Yes.
In order to solve the first one, we can't do
It's going the other way.
That's correct, you get the wrong answer. Did you understand what I meant when the hydrogen has to point away from you, no matter if it's up or down?
yeah.
Everybody still okay? Okay, so let's stick with these for a minute. To answer your question about D and L, right? This is D-glucose. Now the reason it's D-glucose has to do with the last part down here. And this is a Fisher projection again. Remember what we were just saying about Fisher projections? Right, up and down goes
Oh,
away from
away.
you and left and right goes at you. What's not shown here? The H's, right? Okay. The only thing that makes things D or L is this known as the penultimate carbon, and it's pointed to the right, which means it's sticking out at you with this Fisher projection. That makes it D or L. Okay. But while we're at it, okay, does this one here have an RS issue? No, because there's only 3 things connected to it, right? Does this have an RNS issue?
Yeah.
Yes, there's 4 things connected to it. And now, since one of this set reflects a structure up and down, let's go through this one because it's complicated enough so that we can introduce to each other a little bit more detail about what constitutes prioritization. Okay? What you have to do is you have to look at all the groups that are attached to it, right? So let's pick the simplest group first. The lowest value is 4. That one is pretty simple, right? The highest value is the oxygen because it's immediately attached to it too, right? Everybody okay with this so far? Any questions? Okay, now we're going to go to the next group. Carbons. Are they both carbons? Yes, so we can't have any value there. There's a hydrogen here, there's a hydrogen here, so that doesn't change anything, right? Then we get an oxygen here, we have an oxygen here, right? And go back. Then we have a carbon here, but what do we do when we have a double bond? We go to that other thing again. That. There's really 2 oxygens attached here. That's the way we define the priority.
Will we be looking at that carbon that you're pointing at?
Say that again?
Would you be looking at that carbon or the one above it? Where the...
I'm going to number these. 1, 2, 3, 4, 5, 6. So what am I looking at?
Are you looking at the... I think you just marked it as a 3rd carbon instead of...
Yes? Okay, here I am right here.
Okay.
That's the one I'm interested in. This is the lowest priority. This is the highest priority.
Yes.
I then go one step further. They're both carbons.
Okay.
So there's no difference because they're both carbons, right? Then when you take one step further, there is a hydrogen here and a hydrogen here. Again, no difference, right? I'm going to take another step. There's an oxygen here, there's an oxygen here, right? Again, no difference, right? Now I'm going to take another step. There's a carbon here, right? But what do I do up here? I got 2 bonds to an oxygen, so I got to go one more time to the oxygen. There's a double bond here.
Yes.
So you go twice to it.
You wouldn't look at the hydrogen that's attached to the oxygen? You won't look at that first before going to the second carbon? Or the...
No, you got to go one step at a time. One step at a time.
No, I get that. I'm just saying you wouldn't look at the hydrogen first that's attached to that oxygen before going down to that 4th carbon.
Oh, no, you always have to look to what's immediately attached to the carbon that you're looking at.
Okay.
You want me to go out here, in other words? No, you just keep going to, this is a group that's attached to a carbon which is attached to the carbon. That's another way of thinking about it. So, just to finish the thought. So therefore, then if I have an oxygen here and I have an oxygen attachment here, and I have an oxygen here and I have a carbon here, which one takes priority? The oxygen. So therefore, if I'm looking at this whole group up here, okay, all right, let me take these numbers out. This is group 4, lowest group, group 1, highest group. Then this group up here has to be group 2, and this group down here has to be group 3. So which way is it going? It's going 1, 2. See, as soon as you got this one, 1, 2, 3, right? You got this kind of a rotation. 1, 2, 3. Well, which way is the hydrogen pointing?
Go towards.
it. So normally this would be S, but now it is.
Oh, it's R.
Very good. All right.
Oh.
I'll do another one. We'll go through some simpler examples, but yeah, that would be less complicated. Yes. Let me use a simpler one. We'll do that. I'll just rewrite the example up here and make it a simple one. How's that? Yeah, I'm gonna put this in OH, and this is an H, and I think we were looking at this next one, right? And over here, we have an OH and an H, and we don't care about this piece down here at the moment, because this is the one that we're interested in, right? So this is really, the rest of it, let's not worry about it, because once we figure this part out, we got it. Okay, let's look at this card, and let's do what your book does. What's it do to a double bond? It puts an oxygen, first it converts it to this, and this, and this, and that, right? And then over here, this is the one that we're interested in. And then we have this one. And then we have the rest of the group, right? Okay, you ready? So we're going to look at, this one is not chiral, right? This one is chiral. Group number 4. There it is. Group number 1. There it is. Now the question is, what's group number 2? Okay, it's this carbon. Because we're going out one step, right? So what's this carbon attached to? Well, it's attached to a hydrogen, It's attached to an oxygen, It's attached to an oxygen, and down here is really another carbon, right? So, everybody see that? No? Yes?
I would do it down to the carbon and not out to the.
I'm interested in this carbon right here.
Yeah.
Okay? So, what's immediately next to it? Okay?
Two other carbon.
Yeah, another carbon. So, if I say, okay, I've gone over here, here's a hydrogen. Go over here, here's an oxygen. If you want me to go one step further,
So either way.
so you're kind of stuck, okay? But the process should be one of going one step at a time. So I gave you a difficult one, but we can do some simpler ones.
Why is it that you have the carbon that goes out to that oxygen back up to another carbon?
Because that represents the fact of this. This carbon has to have 4 things connected to it. Okay? So what we do is we break it down symbolically so that it has 4 things connected to it. All right? So we have a hydrogen, an oxygen, and an oxygen, right? This oxygen has to have 2 things connected to it. So we break it down symbolically. It's connected to a carbon, and it's connected to a carbon.
Aren't you accounting for 2 oxygens in that model as opposed to the other one?
I'm sorry, I didn't hear what you
You're
said.
accounting for 2 oxygens on the diagram on the right as opposed to the other one where you have 1 oxygen?
Right, because I'm giving you the rules by example, that if you have a double bond, whether it's a double bond to oxygen, a double bond to carbon, a double bond to nitrogen, a double bond to sulfur, you go to the element itself, you come back, you say how many times is it connected to that same element? Twice. I got to connect it another time. What's that element connected to? Is it connected to another carbon? I'm going to show that it's connected to a carbon. It has 2 bonds to it, right? It's symbolic only in the sense that we have to assign a priority. And once we assign a priority, that gives us a way of writing a configuration. And once we have that, then we can say this is the right-handed version, this is the left-handed version. Yes?
So the right-hand model isn't a representation of how the molecule is structured more. It gives us a better diagram to be able to follow.
That's correct.
the entire-
That's correct. You're absolutely correct. Now, why is this important? Because, as we mentioned earlier, in the case of biology, okay, one item is very valuable in terms of its chirality to, let's say, reduce painful obstructions. Its isomer is a toxin. So it's a life and death situation sometimes, whether you have the R or S configuration. Okay? You doing okay? Yes?
Can I ask a little bit of a tiny question? In laboratory setting, how do you play with changing the RNS configurations of the molecule?
It's a good question, and the answer is, until, I don't know, a few years ago, maybe more than a few years now, most people couldn't. Okay? But now, there are techniques that allow you to take, for example, a situation, I'll answer the question this way, where you have, you're familiar with column chromatography perhaps, where you have a column of material and you put your mixture on the top and you run solvent through it, and some of the material clings to the column more tightly than other materials so that you can separate out the pieces. Well, that's okay, except it doesn't do much for you when you have R and S. It seems that they come out the same place because they're chemically many times identical. Well, they're only identical so far as common solvents and common binding sites are concerned. If you take the material that's the solid in there and you have spent a month with your favorite goat and you gave it antibodies to produce to that particular material, and then you bled the goat for a little bit because you don't want to, and then collected the antibodies and did this for a month or so. Now you have antibodies that are binding only one stereoisomer and not the other. Or one binds more tightly than the other. And so now you can get one, you get the R to come through and the S stays behind. There are other techniques besides goat antibodies, but that's an example. There are other examples. Did you get that book of dope? Okay. Now, here are some other issues that you need to consider, and that has to do with the items related to stereogenic centers and R and S. Any questions on this so far? I know I'm talking a lot, but I figured I need to get some of this in front of you so that you can at least know the rules. If we have a structure that has 4 different things, then you know that it is chiral. But with some structures, as you can tell with glucose, we can have more than one center. So if we have a center, and this center, for example, and we're going to use this as let me use this as a Fisher projection so you get very comfortable with this. So here's a Fisher projection. And over here, we're going to have a CH3. Over here, we have a CH3. Over here, we're going to have a BR, BR, H, and H. Okay? First, a simple question. It's almost trivial. How many stereo centers do we have? Now, given what you know right now, you could define each one of them as R and S. Let's do it, just to make sure that everybody can do it. Okay? Let's take this one, for example. Lowest priority group is?
The H.
That's right. Highest priority group? Bromine. Okay, let's go. Oops. Okay. Now let's go to the next. Remember, we're on this carbon, right? We go to the next carbon. It has a hydrogen. I'll even extend this a bit. These are all hydrogens, right? It has. We go from here to here. This has a. This is a carbon. This is a carbon. There's a hydrogen. A hydrogen. A hydrogen. A bromine. So all of a sudden, this group right here becomes group 2. So we're really going 1, 2. This is group 3, right? We're going 1, 2, 3. 1, 2, 3, like this, right? So we have this kind of a circulation. Is the hydrogen pointed out?
No,
or away from us?
away from us, so it's going to be S. I mean,
So
towards us.
therefore it is
S.
S. So this particular piece right here is S. Okay, so now let's repeat this little analysis for the second one. Okay. And over here, this is the carbon we're interested in now. This is group number 4. This is group number 1. Now, again, we go through the same analysis, but I think you can see very quickly that this has to be group number 2,
Two.
and this is group number
3.
3, right? So it's going like this, 1, 2, 3, like this, right? Is the hydrogen away or towards us?
Towards us.
Towards us, so
So
normally this would have been
S, but
S, but now it is
R.
R. Okay, so now you see something of interest here. What you're basically seeing is that the top half of the molecule and the bottom half of the molecule are mirror images of each other. Okay, so here is the top half, and they could look. So the top half and the bottom half are mirror images of each other. So there are 2 centers, right? They have 2 chiral carbons, but this particular molecule, all right, has as its mirror image its bottom half, right? This kind of a molecule is known as a meso structure, which means in Greek to cut in half, and the half is the mirror image of the other one. Okay? So now you're familiar with a meso structure. Doing okay? Questions?
If we're talking about a carbon that doesn't have a hydrogen on it, let's say in the case of the one you just drew, it has the methyl group of bromine and the nitrogen on it,
Okay?
then we would consider the methyl group as the lowest priority, and that would be the 4, and we would do our differently.
Yes, so to answer your question, if you had this, and I don't know, what do you want to put, get the same thing? I'll put a bromine here. You want to put, let's just put a CH2OH here, for example, okay? So what's the smallest priority group here?
The methyl group on the top?
Yeah, the methyl group on the top. This is a very high priority because its atomic mass is very large. The second one is this one. Then the next thing is we have carbon and carbon, hydrogen and hydrogen, then all of a sudden we have an oxygen over here, so that makes this one the next value group, so this would be 1, 2, 3. Is this pointing at us or away from us? What? It's pointing away from us, so therefore it would be 1, 2, 3, and that means it is S.
So I guess my question is more directly, it doesn't always have to be a hydrogen.
No, it does not always have to be a hydrogen here. Absolutely correct. Just the lowest priority group.